On the previous video, I have discussed the wave interference. This time, I will be discussing with you what is photoelectric effect. So without further ado, let's jump into it. When light shines on a metal, electrons can be ejected from the surface of the metal in a phenomenon known as the photoelectric effect. This effect is also often referred to as photoemission, and the electrons that are ejected from the metals are called photoelectrons. In terms of their behaviors and their properties, photoelectrons are no different from other electrons. The prefix photo simply tells us that the electrons had been ejected from the metal surface by incident light. Albert Einstein proposed that light sometimes behave as particles and electromagnetic energy, which we now call photons. The energy of photons could be calculated using the Planck's equation. So we have here the formula, which is the energy of photon is equals to hv, where E photon is the energy of photon in joules and Planck's constant, which is H, 6.626 times 10 to the power of negative 34 joules, and V is the frequency of light in hertz. According to Planck's equation, the energy of photon is proportional to the frequency of light. The amplitude of light is then proportional to the number of photons with a given frequency. Now, as the wavelength of photon increases, what happens to the photon's energy? According to Planck's equation, the energy of photon is proportional to the light frequency. So we have here, which is E is equals to hv. The light frequency is inversely proportional to the wavelength, and that is the symbol of lambda. C is equals to lambda v, where c is the speed of light. That means that increasing the wavelength decreases the light's frequency. Therefore, as the wavelength of the photon increases, its energy decreases. We can think of the incident light as a stream of photons with an energy determined by the light frequency. When the photon hits the metal surface, the photon's energy is absorbed by an electron in the metal. As you can see in the graphic, it illustrates the relationship between light frequency and the kinetic energy of ejected electrons. The frequency of red light on the left is less than the threshold frequency of the metal, so no electrons are ejected. The green in the middle and the blue on the right have greater threshold, so both cause photoemission, or they were able to eject the electrons. The higher energy blue light ejects electrons with higher kinetic energy compared to the green light. Scientists observed that if the incident light had a frequency less than the minimum frequency, then no electrons were ejected regardless of the light amplitude. This minimum frequency is also called the threshold frequency, and the value of threshold frequency depends on the metal. For the frequencies greater than the threshold frequency, electrons would be ejected from the metal. Furthermore, the kinetic energy of the photoelectrons was proportional to the light frequency. The relationship between photoelectrons' kinetic energy and the light frequency is shown in the graph here. Because the light amplitude was kept constant as the light frequency increased, the number of photons being absorbed by the metal remained constant. Thus, the rate of which electrons were ejected from the metal, or the electric current, remained constant as well. The relationship between electron current and the light frequency is illustrated in the graph B. We can analyze the frequency relationship using the law of conservation of energy. The total energy of incoming photon must be equal to the kinetic energy ejected electron. The energy required to free the electrons from the particular metal is also called the metal's work function. So basically, there is also a threshold for it to work aside from the frequency threshold. The energy required to free the electrons from a particular metal is also called the metal's work function, which is presented by the symbol phi. So we have the formula that E photon is equals to kinetic energy of electron plus phi, or the work function. Like the threshold frequency, the value of phi also changes depending on the metal. We can write the energy of the photon in terms of light frequency using Planck's equation. Energy of the photon is equals to hv equals to kinetic energy of the electron plus the work function. Transposing this equation in terms of electrons' kinetic energy, we can get the kinetic energy is equals to hv minus the work function. We can see that the kinetic energy of the photoelectron increases linearly with frequency as long as the photon energy is greater than the work function. We can also use this equation to find the photoelectron's velocity, which is related to the kinetic energy of electrons as follows. So we have kinetic energy is equals to hv minus function is equals to 1/2 MeV2, where Me is the rest mass of electron, which is 9.1094 times 10 to the power of negative 31 in kilogram. So let's have an example over here. So for the photoelectric effect of copper, the work function of copper metal is 7.53 times 10 to the power of negative 19 joule. If we shine light with a frequency of 3 times 10 to the power of 16 on copper metal, will the photoelectric effect be observed? In order to eject the electrons, we need the energy of the photons to be greater than the work function of copper. We can use Planck's equation to calculate the energy of the photon. So we have here the formula. Energy of photon is equals to hv. So for the h and v, so basically we just have to plug in the values. For h which has the constant of 6.626 times 10 to the negative 34 joule, that will be multiplied to 3.0 times 10 to the power of 16 hertz. That will equals to 2.0 times 10 to the negative 17 joule. If we compare our calculated photon energy, copper's work function, we see that the photon energy is greater than the work function. So we have already the answer. 2.0 times 10 to the power of negative 17 is greater than 7.53 times 10 to the negative 19. Thus, we would expect to see the photoelectrons ejected from the copper. Now, we have the value of the photoelectron and the threshold, or the work function. Now, let's solve for the kinetic energy of the electron. What is the kinetic energy of the photoelectrons ejected from the copper by the light with a frequency of 3.0 times 10 to the power of 16 Hz? We can calculate the kinetic energy of the photoelectron using the equation that relates to kinetic energy of the electrons to the energy of the photon. So now, we have the formula. Energy of the photon is equals to the kinetic energy of the electron plus the work function. Since we are now looking for the kinetic energy, we can start by transposing the equations. Now, from the original formula, we have kinetic energy of the electron is equals to energy of photon minus the work function. We can now insert our known values for the energy of the photon and the work function. So we have kinetic energy of electron is equals to 2.0 times 10 to the power of negative 17 minus 7.53 times 10 to the power of negative 19 joule. That will equals to 1.9 times 10 to the power of negative 17 joule. Therefore, each photoelectron has the kinetic energy of 1.9 times 10 to the power of negative 17 joule. Now, let's have some recap about what we have learned about photoelectric effect. Physicists predicted that increasing light amplitude would increase the kinetic energy of emitted photoelectrons, while increasing the frequency would increase measured current. Experiments showed that increasing the light of frequency increased the kinetic energy in the photoelectrons, and increasing the light amplitude increases the current. Based on these findings, Einstein proposed that the light behaved like a stream of photons in an energy of E is equals to hv. The work function, or phi, is the minimum amount of energy required to induce photoemission of electrons from a specific metal surface. The energy of incident photon must be equal to the sum of the work function and the kinetic energy of photoelectrons, which has the formula of E photon is equals to kinetic energy plus phi, or the work function. Now, let's have a little bit of practice of what we have learned today. When we shine light with a frequency of 6.0 times 10 to the power of 14 Hz on a mystery metal, we observe the ejected electrons have the kinetic energy of 3.23 times 10 to the power of negative 20 joule. Some possible candidates of this mystery metal are shown. Here in the table, we have metals and work functions. For the calcium, we have 4.60 times 10 to the power of negative 19. For the tin, we have 7.08 times 10 to the power of negative 19. Sodium, 3.78 times 10 to the power of negative 19. Hafnium, 6.25 times 10 to the power of negative 19. Samarium, we have 4.33 times 10 to the power of negative 19. Based on the information, what is most likely identity of our mystery metal? So we have to choose between calcium, sodium, tin, and samarium. So in order to identify the identity of our mystery metal, we have to identify the work function. Since we know the frequency of the incident light and the kinetic energy of the photoelectrons, we can find the work function in our mystery metal using the following equations. So we have energy of photon is equals to HV is equals to kinetic energy of electron plus work function. So all we have to do now is to transpose or to rearrange the equation. Since we are looking for the work function, so we have work function is equals to HV minus kinetic energy of the electron. We can plug in our known values for frequency in the kinetic energy of electrons to calculate the work function. So we have work function equals to HV minus kinetic energy of electron. So for the H, we have 6.626 times 10 to the power of negative 34 joules multiplied to 6.20 times 10 to the power of 14 hertz minus 3.28 times 10 to the power of negative 20 joules. 6.626 times 10 to the power of negative 34 multiplied to 6.20 times 10 to the power of 14 is equals to 4.11 times 10 to the power of negative 19 joule minus 3.28 times 10 to the power of negative 20 joule. And the answer is 3.78 times 10 to the power of negative 19. Based on the work function, 3.78 times 10 to the power of negative 19 joule, our mystery metal is most likely the sodium. So that's it, guys, for our photoelectric effect, and I hope you learned something from this and have a good one. Bye-bye.